Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 3, problem 7. The electromagnet shown in this figure, P3.7, can be used to lift a sheet of steel. Okay, we have this coil and this electromagnet. This is sheet of steel. When we excite this coil, we have a lifting force on this load, on this sheet of steel. The coil has 400 turns and a resistance of 5 ohms. The number of turns and the resistance of this coil are given. The reluctance of the magnetic material is negligible. Okay, we can consider the iron parts ideal. We don't have any magnetomotive force drop in iron parts. The magnetic core has a square cross section of 5 times 5 centimeters. So here, let me copy this image. We have this structure. Here the value of the resistance is given. This is 5 ohms. The number of turns is given for this coil, 400 turns. Okay, 400. And the cross section area of the core is given. The cross section is a square. So if we consider this width equal to 5 centimeter, because the depth of the problem is also 5 centimeters, the cross-section area for this air gap is 5 times 5, that is 25 centimeter square. We have the same cross-section area here for this air gap. We have two air gaps, and here it is mentioned that the thickness of these two air gaps are the same. An average force of 550 newtons is required to lift the sheet of steel. For DC supply, determine the DC source voltage. Determine the energy stored in the magnetic field. So, if we need to generate this force, how much should be the value of the DC source voltage, right? Here we know the resistance of the coil and the number of turns. In the previous problems, we calculated the force assuming a proper value for the air gap flux density. For example, in this problem, we assume a proper number for the flux density and air gap, and we calculate the force. But in this problem, the required force is given, and we need to calculate the flux density in air gap, the required coil current, and finally the required DC source voltage. So how we can do that? Here in this structure, this is the positive terminal of the DC supply. This is the direction of the current in the coil, and we will have this field generated by this coil. If I plot this flux line in the middle of the structure, okay, we can use this equation to calculate the required value for the coil current. Integral of H dot dl is equal to Ni. So because the iron parts are ideal, we don't have any magnetomotive force drop, right? For this flux line in iron parts, we have these two air gaps in front of this flux line. This is one air gap, and this is another one. Okay, so we can write H gap, the value of the magnetic field intensity in the air gap, times 2 times gap. The air gap thickness is 1 millimeter. Okay, this is equal to Ni. So instead of H gap, we can write B gap divided by mu 0 times 2 gap is equal to Ni. We are looking for the value of the current. We know the number of turns, we know the air gap thickness, we know the value of the permeability of the air, but we don't know the value of the B gap. How we can calculate B gap? Using the force equation. Okay? The force, the lifting force is equal to B gap to the power 2 divided by 2 times mu 0. This is the right, the value of the force density times the cross section area. So this is the cross section area for two air gaps. Okay, according to this equation, what is the value of the B gap is equal to a square root of force times 2 times mu 0 divided by the total area of the air gap, the cross section area. The value of the force is 550 newtons. 2 times mu 0 divided by 2 times 5 times 5 times 10 to the power of minus 4, because these are in centimeters. So the value of the force is equal to this one. And finally, we can calculate the value of the flux density in air gap, that is equal to 0.5258. Here in MATLAB, also I wrote this M file for this problem. Here are inputs: the magnetic permeability of the air, the number of turns for the coil 400, the DC resistance of the coil, the cross-section area of one air gap, and this is the required force. If you consider this variable as the cross-section area of one air gap, this is equal to a gap, one air gap. So I should modify this equation. I write here 2 times the Ag in this case. So not important. We know that this is the total air gap area, but you can rewrite this equation in this form. Anyway, so in this case, we have this force, and this is the air gap thickness in millimeters. I implemented this equation here. If I run the code, here you can see the value of the B gap, 0.5258 Tesla. And when we know the value of the B gap, we can calculate the coil current using this equation. I implemented this equation here. If you replace the numbers, the value of the coil current will be equal to 2.09 amps. Yes, this is the value of the coil current, this equation. And finally, we can calculate the value of the DC voltage, the required DC voltage, that is equal to R times I. So, why we can write this equation? Because the current is DC. We don't have any voltage drop on this inductor in a steady state case. okay, not transient. So you know that the voltage drop on inductor is L di dt. So when we have DC current, we don't have any voltage drop. This point is important, and in the next part of this question, we will calculate the required voltage in the case of using an AC supply. So you can realize the difference. So the value of the DC voltage is 10.4 volts. This number VDC required DC voltage. And in the next part, how we can calculate the energy stored in the magnetic field using this equation. This is the energy density, okay, times the volume of the air gap. So the value of the B gap is 0.52 Tesla divided by 2 times mu 0 times the total cross section area of air gaps times the air gap thickness, because in this case we are going to calculate the volume. The thickness of the air gap is 1 millimeter. We should multiply it by 10 to the power minus 3 to have it in meter. And this is 25 centimeter square, 2 times this area, and we should convert it to meter square. The stored energy in the magnetic field is 0.55 joule, this number. Okay. Also, you can calculate the energy stored in the magnetic field using this equation. Yes, I calculated this number using another equation just for comparison. Okay, so you know that we can calculate the energy stored in a linear system. Okay, using this equation, 1 divided by 2 flux linkage times current, or using field quantities. Okay, this equation. So here, instead of flux linkage, you can write NBA, number of turns, flux density, cross section area, and this is the current. If you replace the number, we will have the same value here, 0.55 joule. Let me check. Do we have the solution for this problem or not? Yes, we have numbers 10.4 volts, 0.55 joule, okay, for the energy stored. Now let's solve the part B for AC supply at 60 Hertz. Determine the AC source voltage. Okay. So in the part A, we used a DC voltage source. And if we want to use an AC voltage source, how much should be the RMS value of the source voltage? If we are going to get the same amount of the force applied on the load, so we need to have the same current. For the AC is RMS, for the DC is the DC one. So here in reference also we have a similar example. Here you can review this important example here. Example 3.4. Okay, the same structure that we have. So as you can see, when we apply an AC voltage source, this will be the variation of the B in air gap. This is the current and this is the force. Okay, these quantities are in the same phase. Yes, this is also important. So this is the value of the force. We can calculate the RMS value of the force. And if we set the RMS value equal to 550 Newton, that is equal to the DC voltage source, we need to have this RMS value for the current that we calculated it here, 2.09. Yes, the force is proportional to the BRMS to the power 2, or actually this one. So in this case, if we have this RMS value for the current, how much is the RMS value of the voltage? We need to calculate the impedance of this coil. So what is the value of the coil inductance? Is equal to the N to the power 2 divided by the reluctance. The reluctance is equal to 2 times gap divided by mu 0 times the air gap area, 1 air gap. Okay? If you follow this flux line, we have 1 air gap reluctance here, 1 air gap reluctance here, right? 2 times gap divided by mu 0 A. This is the net reluctance in front of this flux line. So the value of the coil inductance will be equal to 0.25 henries. What is the value of the coil impedance? R plus j omega L. R is 5, j 2 times pi times 60 hertz, the frequency of the supply. So times the coil inductance. The amplitude of the impedance is equal to 94.8. And finally, if we multiply the amplitude of the impedance by the RMS value of the current, we can calculate the RMS voltage here. That is much higher than the DC voltage. Okay? So the DC voltage, the required DC voltage is 10.4. And the required AC voltage is 198. Because of this reactance, we should use a much higher voltage. So this is why lifting devices use DC voltage. Okay, so this point is also mentioned here. Okay, the lifting magnets are normally operated from DC sources. Yes, this is the point of this problem. Now let's go for the next problem, problem 8. The features of a moving iron ampermeter are shown in this figure. A structure of an ampermeter here to measure the current. These are terminals. When current flows through the curved solenoid coil, this coil, a curved ferromagnetic rod is pulled into the solenoid against the torque of a restraining spring. So here we have this spring, right? In center, this is the ferromagnetic rod, and this is the solenoid coil that is stationary. This is the scale. The inductance of the coil is given here. This function, we have a constant term and a term that varies with theta, right? The angle, where theta is the angle of deflection in radians. The spring constant is also given here, that is in Newton meter divided by radian. Here, as you can see, the unit is the unit of the torque. Okay, Newton meter. Okay, so let me copy this image here. This is the structure of the ampermeter. When we have current in this coil, the ferromagnetic rod moves in this direction. This is the angle of deflection. theta. Okay, and this is the force applied in this direction, or actually we should say that torque by the spring, okay, in this direction. How much is the value of the torque applied by this spring is the constant of this spring, ks times theta. This is in opposite direction. The value of the ks is given here, 0.65 times 10 to the power minus 3. Okay, 0.65 times 10 to the power minus 3. This is the value of the spring torque, and the value of the coil inductance is given. We should calculate the magnetic torque, then we can do the calculations and calculate the value of the theta as a function of the RMS value of the current. So anyway, let's check the parts of the question. Show that the ampere meter measures the root mean square value of the current. We can have DC or AC currents or arbitrary waveform for the current in this coil. What is the value of the torque? Here in this section, rotating machines, we have equations for calculation of the torque. Before this section, right, until this section 3.4, we discussed equations for calculation of the force. But when we have rotating objects in the structure, we can use energy formulation, the same formulations, to calculate the torque in this case instead of force. Here in this figure 3.6, we have this structure, this stator, and this rotor. This is a rotating object. Also, we have two coils, the stator coil, and this is the rotor coil. As you know, again, we can write this equation. When we excite these two coils, how much is the change in the value of the stored energy in the magnetic field? Is Es times Is dt, energy delivered to this coil, this stationary coil, and Er times Ir dt, the energy stored to this coil, energy delivered to this coil. So this is the summation. The total energy change in the magnetic field is Is d lambda Ir d lambda. We have this matrix equation, the relationship between the flux linkage for these coils and currents. In this case, because we have two coils, we have also this mutual inductance, LSR. Okay, lambda S is LSSIS plus LSRIR. We should consider the mutual inductances between these two coils. So we have this matrix equation. If you replace the values of lambda S and lambda R in this equation, this will be the change, dWf. Okay? So finally, if you calculate the integral of this expression, we will have this equation. The total energy stored in the magnetic field for this structure that we have two coils, two excitations, is 1 divided by 2 LSS, the self-inductance of this coil to the times is to the power 2 plus 1 divided by LRR IR to the power 2 plus LSR times ISIR. And how much is the value of the torque? We can take the partial derivative with respect to theta. Okay, so the value of the force is a partial derivative with respect to position coordinate. Here we use the angle coordinate. So in this case, if you take the partial derivative, we will have this equation for the torque. So we have three terms. If we have variation for self-inductance of the first coil versus theta, we will have this. Also, this is called the reluctance torque. Okay, the reluctance torque, this one or this one, when the LSS is a function of theta or LRR. Anyway, so in this case, in this ampermeter, we have only one coil, and the value of the inductance as a function of theta is given here, 4.5 plus 18 times theta microhenry. What is the value of the magnetic torque? Okay, the value of the current of this coil to the power 2 times dl d theta. The same equation here. In this case, we don't have IR, only we have one coil. So if you replace the numbers, take derivative of inductance with respect to theta, this is constant term, will be 0, is 18 times 10 to the power minus 6, because this is in microhenry. So we will have this equation. This is the value of the torque as a function of current. What is the average value of the torque? The average value of the torque is the average value of this expression. Or actually, you know that the average value of this function, the average value of this function, I to the power 2, we can write it in terms of its RMS value. So the average value of the torque is 9 times 10 to the power minus 6 times the RMS value of the current to the power 2. So the ampermeter measures the RMS value of the current, right? For any waveform for the current. In equilibrium condition, how much is the value of theta? So the part B, determine the deflection in degrees for a current of 10 amperes. When the value of the current is 10 amperes, the RMS value, right? We don't know what is the waveform of the current. Is it DC, AC, or arbitrary waveform? The RMS value of the current is 10. How much is the angle of the deflection here for this arrow? In equilibrium condition, we can write Ts, the torque of a spring, that is Ks theta, must be equal to the magnetic torque. Okay, this torque must be equal to the magnetic torque in equilibrium condition. So this is equal to 0.65 times 10 to the power minus 3 times theta. This is the value of the magnetic torque. If you replace the numbers, the current equal to 10, the RMS value, the angle of the deflection will be equal to 79.3 degrees. Okay, so you can redo the calculations. Part C, determine the voltage drop across the ampermeter terminal when 10 ampere RMS at 60 Hz flows through the ampere meter. So when we have this current, and this is the frequency of the current, we have AC current. The coil resistance is also given here. For this condition, how much is the value of the voltage drop? You know that the value of the voltage drop for ideal ampere meter must be 0. Okay? But in real case, we don't have ideal ampere meters. So in this condition, as you can see, again, like before this for this problem, we should calculate the impedance of the coil to calculate the value of the voltage drop. The impedance of the coil is R plus J omega L. What is the value of the coil inductance? We calculated the angle of the deflection. So if you replace it into this equation, this will be the value of the coil inductance, and this is the value of the coil impedance, the resistance plus reactance, the amplitude. You can calculate the amplitude here, and finally the RMS value, the value of the voltage drop on this coil will be equal to zero point 0.2 volts. Yes, this low number, but in ideal case, this number should be as low as possible. You know that for ideal ampere meter. Anyway, you can redo the calculations, solve this problem, and review these points that we have. Let's go for the next problem. Problem 9. A reluctance machine of the form shown in this figure 3.6 has no rotor winding. The inductance of the stator winding is given here. So let me copy this, okay, and paste it here. In this problem, we have a structure like this, but we don't have the rotor coil. Only we have one winding, the stator winding, and its inductance is given here. This function, we have a constant term and these two varying terms, cosine of 2 times theta and cosine of 4 times theta. A current of 10 amps at 60 hertz is passed through the stator coil. A. Determine the values of speed omega m of the rotor at which the machine will develop an average torque. In this case, in this problem, because we have only one winding, the value of the magnetic torque will be equal to this one, the first term. Only we have a reluctance torque, okay? Due to variation of the self-inductance of the stator winding with respect to theta. Okay, so this is the value of the magnetic torque. And for this structure, only for specific values of the rotor speed, we have average mechanical torque. Okay, so in the part A, we should find speeds that we have average mechanical torque, average reluctance torque. This is an important problem. Okay, in the next chapters, when we investigate properties of different electric machine types, so we investigate this feature again and again for induction machine, synchronous machine, DC machine. Okay, so in this case, we have a simple reluctance machine, a rotating machine. We have a rotating object here. We have two important parameters. Yes, the frequency of the current This is electrical frequency, frequency of electrical parameters. For an electric machine, we have voltage and currents. For the windings, electrical parameters, we have torque, right? Electric torque, magnetic torque, and we have a speed, mechanical speed. This is angular speed or mechanical angle. We have mechanical parameters, electrical parameters. So in the case of AC, yes, in the case of harmonic analysis, harmonic components, we can have electrical frequencies and mechanical frequencies. So here, if we set the frequency of the current equal to 60 hertz, or in equivalent term, omega e, we can have it in angular speed, radian per second. For what values of omega m, we have mechanical torque, right? So this is the mechanical angular speed of rotation of this object. So in this case, the value of the magnetic torque is 1 divided by 2 I to the power 2 times dl d theta. You can take derivative of this inductance function that is equal to this one. For the current, I can assume this function. The RMS value of the current is 10. Its peak value is a square root of 2 times 10. The peak value times sine of omega et, electrical frequency, okay, or electrical angular speed. This is the amplitude of the current times sine of omega et. What is the theta? Theta is this angle, the angle of the center axis of this moving object with respect to this axis, that is for the state or the stationary part. I can assume this right function for it, theta equal to omega m, the angular mechanical speed, times time plus delta. Delta is the value of theta when the time is equal to 0, right? Initial position of this moving object before applying current to this coil. Yes, delta is theta for t equal to 0. So in this case, if we replace the value of the current, we will have this. And if we replace the value of theta, we will have these two terms. The next step is just trigonometry, simplifying this expression. How we can simplify this expression? Here, you remember these important trigonometric equations. Okay? In this problem, I am going to use this equation and this equation. In the next problem, I use these equations. Equivalent, right? Just trigonometry. You should simplify the expression. We have these important equations. You should keep these equations in mind for exam when we have problems like this and you need to simplify these expressions. Anyway, so we have these two important terms. Let me copy this. We have these two important terms. We should multiply this term by this one and also multiply this with this function. Here I considered this case, this one, so we can use the same procedure for the next one. How we can simplify this product, sine of omega et to the power 2 times sine of 2 times omega mt plus 2 times delta. this is equal to this one. Okay, if I use this equation first, we have this, and again I can repeat the product and use this equation, sine times cosine. Okay, finally if you simplify this expression, we will have this 1 divided by 2 times sine of 2 times omega mt plus 2 delta plus these two expressions. So what is important here is that we have three terms. In the first term, we don't have omega e, the electrical angular speed. Okay? In this term, we have omega e and omega m. The difference between the omega e and omega m is important here. In this term, we have omega e and omega m, and their summation is important. In all terms, we have delta. Okay, so this is the simplified version of this product. But here in this case, we have two terms, 2 times omega m, and here is 4 times omega m. Finally, if you repeat the same calculations, we will have this equation for the magnetic torque. Okay, these two terms, we have six terms, right? We have this term, it has three terms, and three terms here. In total, we have six terms. So, according to this expression, for what value of the omega m we have average electric torque? Yes, in the first case, we can assume omega m equal to 0, right? 0 speed. Let me write this here, 0. When the value of the omega m is 0, this is sine of 2 times delta. And this is sine of 4 times delta. Here, omega m is 0, 0, 0, 0 here, but we have omega e, and you know that the average value of these functions will be equal to 0. So when the value of the omega m is 0, the average value of the electrical torque, right, the electromagnetic torque, is equal to this expression. It depends on delta only, the initial position of this moving object. So, what about other speeds? When the value of the omega m is equal to positive omega e, yes, omega m is equal to omega e, this term is 0. Yes, but here we have omega m. The average value of this term is 0. This term is 0. The average value of these terms are also 0. We have this. Okay, this is the average value of the torque. This case, when omega m is equal to positive omega e or negative 1. In the case of negative 1, we have this function. Okay, in both cases, omega m equal to plus or minus omega e, we have this average value for the torque. This is delta, the initial position. What is the maximum torque? Maximum torque is this one, 15 Newton meter. And also we can calculate the maximum power. In this case, the maximum power is equal to torque times omega m, mechanical angular speed, not electrical one, when we are going to calculate the mechanical power. Okay, that is equal to 5655 watts. So also let me write 0 here. In the part A, we should calculate the maximum torque, the average torque, and here in the part B, we should calculate the maximum torque and the maximum developed mechanical power. So yes, here was calculations for the omega e, the first case. So here, yes, we have this equation. The next one, when omega m is plus or minus omega e divided by 2, if you replace this in this term, yes, we will have this average value. The rest are 0, average value of the rest. And when omega m is negative omega e divided by 2, if you replace it in this function, this will be the right, the average value of the magnetic torque. What is the maximum value of the torque? 20 newton meters. The maximum power is equal to the torque times omega m. That is equal to this one. So let me check the solutions. I think we have solutions here. Yes, this is the part A, 377 radian per second for this speeds, and this speeds we have average torque. Yes, let me calculate 2 times pi times 60, 377 divided by 288. Yes, these terms that we calculated, the same numbers we have here. For the first case, the maximum torque is 15. This is the power we calculated. And this is for the second case, when this is the mechanical speed. So we have these two numbers. And the next part, determine the maximum torque at 0 speed. When the omega m is equal to 0, the average value of the torque is equal to this one. How we can calculate the maximum average torque for 0 speed? We should take derivative of this expression with respect to delta, which is this one, equal to 0. We can solve this equation analytically or numerically to find delta. As you can see here, for this value of the delta, we have the maximum torque. The maximum torque is equal to 62.45, this number. Okay, so you can plot this function. You can plot this function to find the delta. Let me write this M file here for this problem. Problem 9. Okay, let's change the value of delta from line space from 0 to pi divided by 2. Consider 1000 points. What is the value of Tm? The magnetic torque is equal to 30 times sine of 2 times delta plus the next term, 40 times sine of 4 times delta. So we can plot delta and Tm. So let's run the code. Here, as you can see, we have this variation for the value of the torque. Let me check this expression again. Okay, here this is pi divided by 2. So yes, this is the developed electric torque. You know that the X label is the initial position of the rotor, delta. We can have it in degrees or radian. In degree, let me multiply this by 180 divided by pi. And the Y label is the magnetic torque, TM. The unit is Newton meter. So let's run the code again. Here we have maximum torque. You can see the value of the delta, 25.8. Yes, this number. The maximum value of torque is 62.45. So this is important. As you can see here, the initial position of the rotor is important and it determines the maximum average torque that we can get for this structure. Okay, so here for this problem, I am going to consider arbitrary dimensions and do a simulation in ANSYS Maxwell just to show the variation of the inductance for this coil that we have. So let me save as this project to right this folder problem 9 and delete this one. How we can generate a structure like this one for this problem to investigate, right? How we can calculate the inductance of the coil. Let's use these arbitrary numbers. Here, I am going to consider these dimensions. This rectangle X size, let's consider 2 times width of the yoke plus width of the window. Width of the yoke, let's consider 30 millimeters or 3 centimeter. Width of the window equal to 8 centimeters. So the Y size the same. Okay. This rectangle, let's subtract this one. This is width of the yoke, width of the yoke and 0. Width of the window, width of the window. You can realize these parameters that we are using. Okay, so here are dimensions that we have. This is the width of the yoke or width of the iron, width of the yoke, and this is width of the window. I use the same numbers also for horizontal limbs. So in this case, how we can generate a structure of the moving object. Let me increase this number to 10, and here we can draw this circle. First, let's change dimensions. The center point of this circle, the x coordinate, must be in center of this limb. You know that the distance of this point from the origin, the x distance, is width of yoke plus width of window plus 0.5 times width of the yoke, the x distance. We have this distance also for the y. Okay, this one. This distance for the y, that is width of window divided by 2 plus width of the yoke. Okay, so x size is 1.5 times width of the yoke plus width of the window. The center point, the y coordinate, is width of the window divided by 2 plus width of the yoke. What is the radius of this circle? I am going to write this one. The radius of the moving part. Radius of the moving object, the moving part. Let's consider it equal to, again, 3 centimeters. Okay, this one. And let me draw another circle here. Let's copy this expression. the same center. Here I am going to use this one, radius of the moving part plus the gap. The gap equal to 1 millimeter. Okay, the air gap thickness. So here we have two circles. So this circle, circle 2, let's select this rectangle, circle 2, subtract, yes. Okay, and now let's write, draw another rectangle and make it intersection with this one. In this case, if I draw this coil, this one, this coil here, let's set dimensions like before, you know that. The x position is width of the yoke plus, let's consider 2 millimeters. The y is the same. This is width of the coil equal to 1.5 centimeters. This is width of the window minus 4 millimeters. Okay, this coil arm, let's duplicate and mirror it here. This one, this is the width of the yoke divided by 2. Anyway, so consider this structure. If I select these two rectangles, change the color and set the material to copper, okay, and let's define one excitation for these two regions. Here, let's assign this excitation number of turns times coil current. Number of turns equal to, let's consider 200. This is unitless. Coil current equal to 1 amps. Yes, we have defined this excitation. Let's copy this. For this region, assign excitation in the negative direction, the same excitation. So these two excitations that I defined for this coil. What do you think? If I excite this coil and rotate this object, we don't have any reluctance torque, right? Because the reluctance in front of this coil is constant. What is the equivalent circuit, the magnetic equivalent circuit of this structure? Is this one. We have one magnetomotive force, Ni. We have this reluctance for the iron, reluctance of the core for the stator. Let's write reluctance of the stator. We have this reluctance for the stator. We have air gap reluctance, one air gap reluctance here. We have this reluctance for the rotor, and again one air gap reluctance here. Okay, reluctance for the rotor and one air gap reluctance again here. So in this case, because the value of these reluctances are not functions of theta, so the value of the inductance is only a function of current. In linear case, is not also a function of current, it's just a function of the structure that we have, that is a constant number. But as you can see here, if we are going to have magnetic torque, the inductance should be a function of theta, otherwise this derivative is zero. We don't have torque. In this structure, we don't have reluctance torque. Okay, so if we have a structure in such a way that the reluctance of the gaps, rotor and this gap, are functions of theta, yes, we have reluctance torque, like this one in this case. So let me assign this material M 530 50A. This material, let's set the properties of the material. We have the HP curve of this non-magnetic material here. The composition, I'm going to use laminated electric steel. The stacking direction V3. The stacking direction is in the direction of the z-axis. You know that we discussed this point before. So now let's draw the region offset equal to 100%. And from here, let's select this edge to apply boundary condition, zero vector potential boundary condition. This is the rotor. Let's change the names. Rotor. This is the stator. Stator. And we have these two coil arms. This is the coil arm 1, and this is the coil arm 2. We have these two coil arms. The rotor, stator, coil arm 1 and coil arm 2. We defined boundary conditions, and now let's add the solver solution setup. Let's select these objects and assign mesh operation inside them equal to 0.4 centimeters. So for this structure, if I analyze to calculate the flux density in iron parts, also the flux lines, we can realize an important point. So let's select all objects, the flux lines. Okay, you can see the flux lines. Also rotor stator field, plot the flux density level. Let me increase the value of the current to 5. Maybe we will have a higher value, right, for the flux density in the core. I didn't do the calculations, just I want to visualize the functions, variation of the inductance, and so on. This is important. So in this case, you can see the flux lines and the level of the flux density. Let's change also the color of flux lines, B and flux lines. So how much is the value of the coil inductance in this case? If I define this parameter, the matrix, let's include these two, the number of turns n, we can calculate coil inductance. Okay, so here you can visualize the value. I am going to also calculate the torque. The torque applied to the rotor. How we can calculate that? We should define this parameter. So let's select the rotor, and from here parameters we can assign torque. But in this case we have this option. And when we calculate the torque in ANSYS Maxwell, we should define the center of the rotation. Where is the center of the rotation? This is not the global coordinate system that we have here. Okay, so in this case, this is the direction of the rotation that we have. So because of this, I should define a new coordinate system, create here, offset, and select the center point. So this is a relative coordinate system. Let me hide the enclosure. Okay, so this is better. Here we have these two coordinate systems, this global one and this local coordinate system. Okay, the global and local. What is the coordinates of this local coordinate system? Here I set it is the center of this circle. And when I calculate torque, I should calculate torque considering this center of the rotation. Okay, the rotor rotates with respect to this point. In this case, we can select rotor, assign parameters, calculate torque. What is the axis of the rotation is this relative coordinate system that we define. So you can see this right arrow. This is the axis of the rotation. Now we can calculate the torque correct. Now let's do a parametric simulation. I am going to rotate the rotor. Let's select the rotor, rotate it with respect to which one? X, Y, Z coordinate. Here, first of all, we should select the relative coordinate system. Now this is the active one. So we can then select the rotor, rotate it. Here I write delta. Okay. Did you define delta? No, I am going to define delta now. 0 degrees? Yes. Consider that if you select the global coordinate system and rotate the rotor, so the situation will be different. If I write 5, yes, this is the rotation. That is not correct. So let me delete the second rotation that we defined here. Okay, so let's delete it. Now this is the correct rotation. The coordinate system is relative coordinate system 1. Anyway, so let's rotate the rotor and perform a parametric simulation. In Optimetrics, I define a parametric simulation. Let's add delta. I'm going to change the delta from 0 to 90 degrees or from 0 to 360. The step size, consider 18 degrees. So, yes. Again, save fields and mesh data. All calculations are the same. Yes, let's clean up the solutions and run the simulation. In this case, we are changing the value of delta and rerun the magnetic simulation to calculate inductance and torque. So, Optimetrics, let's analyze the problem. So, what do you think? In this case, we don't have any variation in the value of the reluctance as a function of theta. So the value of the inductance, the coil inductance, as a function of delta or as a function of rotor position is constant. Also, what is the value of the torque? You will see what we calculate for the torque. The value of the torque is 0 in this case, right? We have a round rotor. Okay, simulation completed. Now let's realize the solution. Here, let me select all faces, flux lines, select the rotor and stator, plot B mag. These two. Okay. Right click on parametric analysis, view analysis results. Let's select the first variation, the second one. Okay, so you can check the solutions. In this case, if I change the value of delta, I can even make animation. Okay, I can generate animations. I will do that later. In results, magnetostatic rectangular plot, let's plot the torque as a function of delta. Yes, millinewton meter. The value is 0. So the depth of the problem in this case is 1 meter. I didn't consider depth of the problem is 1 meter, so not important for this qualitative analysis. So here, as you can see, the value of the torque is equal to 0, a very low number. Okay. And what is the value of the inductance? The magnetic flux or inductance of this coil as a function of delta. Here, as you can see, is zero point 0.9 henries. This is a constant number because let me set the scale, the minimum value equal to 0. This is a constant number. Okay, we don't have a variation for inductance as a function of rotor position. Yes, even here, if I generate animation, let me from Maxwell 2D fields generate animation, select the parametric setup one, this parametric setup that we did. Yes, so okay. In this case, the software changes the delta and generate this flux density plot. Yes, because the rotor is moving in this case, but because we don't have any reluctance change, as you can see here, we have these fixed flux lines. So we didn't have any reluctance torque. And now in the new case, let's consider a saliency for the rotor. And if I add this new rectangle here, okay, select the rectangle tree that we added, the rotor first, and this rectangle tree intersect. In this case, we have reluctance torque because when we rotate the rotor, we have the change in the value of the air gap reluctances. So let's clean up the solutions and analyze the parametric setup. Not setup one, excuse me. Let's abort this simulation, clean up the solutions again, and run this parametric analysis. In this case, we change the rotor position. Here we have a saliency for the rotor. So we will have a reluctance torque and we will have variation in inductance. In this problem, the variation in the value of the self-inductance is approximated using this equation. And we did these calculations considering this function. So in ANSYS Maxwell, let's check what is the waveform of the variation of the inductance for this coil when we have this moving object. This is the value of the inductance. So let me check the variation of the inductance. Yes, this is for the new solution, variation versus delta. So here, if I, okay, let's generate animation and then we will check the functions. The parametric sweep. So in this case, I am going to check. Yes, we don't have rotation. Okay. What is the reason? Let me check. The rotor, the angle is delta. We should have rotation. So what is the problem? Because I did intersection after the rotation, this is the problem. So let's delete the rotation and select this object, rotate it again. The angle is delta. In this case, if I set delta equal to 5, okay, this is wrong. We should select the relative coordinate system 1. Now this is correct. So delta equal to 50, 90. Yes, now we have correct rotation. So again, let's clean up the solutions and run this parametric analysis. Yes, because I did intersection and generated this geometry. The geometry generation in ANSYS Maxwell is history based. You can see operations in this tree. We should do the rotation as last geometrical operation that we have. So now let's check the numbers. Here you can see the variation of the magnetic torque and the variation in the value of the inductance. Okay, so here if we set the minimum value to 0 again, you can approximate this function with a cosine function. We have a constant value, average value for this function. What is the average value? Is 458, the average value of this function, and we have this variation. You can use Fourier series, right? You know that we have cosine of 2 times theta, cosine of 4 times theta, and we have these harmonics. Only 2 harmonics are included in this equation. Okay, the variation of the inductance, and this is the variation of the magnetic torque when we change delta. In this case, again, we can generate animation considering this parametric setup. Yes, we should generate the figure first, then we can generate animation. So as you can see here, when we change the rotor position, rotor angle, we have change in the value of the reluctance, change in the value of the flux lines, and in this case we have reluctance torque. Perfect software, you can generate this kind of animations. Okay, even you can export this animation, okay, in different formats. Perfect. You can do a similar simulation in ANSYS Maxwell to generate these graphs, variation of the inductance versus the rotor position, the delta. In this simulation, I considered constant current and changed the rotor position to find this function. But to calculate the average torque and considering an AC current, we should do transient simulations, right? Out of the scope for this video. So let's continue solving the next problems in the next video.